Hi, my name is Carlson. I'm one of the senior FAEs here at Altium, and today I would like to discuss with you engineering a layer stack up for high-speed design. Now, much has been written on this topic, and I'm by no means going to be comprehensive, but I would like to show you a few of the features that you need to consider when developing your layer stack up, again for high-speed design. Now, here I have a typical 6-layer stack up that would be appropriate for high-speed design. So let's look at some of the features of this. So the black lines represent pre-preg material, the blue lines are core material, and the orange is obviously my copper layers. I have 2 planes and 4 routing layers. Now, for your high-speed signals, these need to be very tightly coupled to a plane layer. So this core material needs to be as thin as possible, and we need to use core here because this is going to be impedance driven. So we need a very flat surface to guarantee that we have consistent impedance down the length of our routed traces. Then our outside layers are pre-pregged to the entire stack up. Now these are suitable for your low speed type signals, your analog signal processing, and anything else that does not have to be impedance driven. Then we use pre-preg material at the center of the stack up to build up the stack so that we have the appropriate final thickness of our board, generally 62 mils. Now, when you're developing this layer stack up, you need to work with your fabricator. You need to understand the materials that they normally stock. I made this mistake one time. I engineered a layer stack up without considering what they have on the shelf. They built the board the way I specified, but they had to special order some of the materials, and it added significant cost to the overall board. Okay, another thing you need to consider are your via stacks. Now, in looking at this layer stack up, this upper portion and this lower portion could be created as subassemblies. These could be placed on a drill machine. They could be drilled and plated individually. So we could use blind vias from the top layer down to our first high-speed signal layer. However, what about this layer? Once this has all been laminated with the pre-preg material in the center, that's a difficult layer to get to. That's going to have to be laser drilled and plated, adding significant cost to the overall design. So the most inexpensive way to design this board would be to use through-hole vias. Now, with your through-hole vias, those will go completely through the layer stack, and then we will bring out an annulus on each of our copper layers. Now, there's a problem with this, in that when we're routing from a top layer to our second signal layer, we have this via stub left over here. And the problem with that is that adds parasitic capacitance to our signal. So if we were to draw a single-ended signal here, we would have parasitic capacitance to our AC ground. Now this can be as much as a half a picofarad. This value is obviously going to be determined by the physical characteristics of our via, but this can really affect our signal integrity. So the approach we use when using through-hole vias on high-speed design is we back drill this via barrel to remove it. So we would take a drill that is slightly larger in diameter than the via barrel, and we would drill this material out. Now, when you do this, this isn't adding a lot of extra technology to this, in that we don't have to do any laser drilling to plate to vias that are difficult to get to. We simply use all through-hole vias, most cost-effective approach, and then back drill those particular vias as necessary. If you have questions about this topic or have other topics you'd like to see us present, please leave your comments in the comment section below. I'm Carlson. Thanks for your time.